what I'm going to talk about is passwords and how to store passwords in the database, and more importantly, how to crack them. The database is stored. So, this company called RockU was founded in 2005. It's a Facebook widget company. They created small widgets, various types of widgets, and for Facebook, and became very popular in few years. So in 2009, there was a data breach. Right? Some hackers got hold of their database through SQL injection attack. So their entire database was stolen. Right? It contained 32 million user accounts. All these user accounts were exposed to outside world. Later, people found out that the person who hacked this database, he publicly posted the entire user list with the passwords. It was found that they were storing passwords in the database in plain text, right? Instead of hashing. 32 million users. They still had 32 million users, and they were storing passwords in plain text, right? RockU. That's the company. So we have some interesting data by analyzing their password list. This is the password length. So 25% of those passwords were about 6 character long. Right? 20% was about 7 characters long. This is how the password lengths are distributed. This is about the composition of the password, right? Is 1.62% only uppercase, and 41% only lowercase, 15% only numeral, only 36.94% use mixed letters and numerals, right? Only 3.8% contain special characters. Both the company and their users are alike. When you look at this. So these are the top 10 passwords extracted from their hacked database. ABC12. I love it. Password. Users. RockU is so. This is how people use password. Most of them. So these people, the RockU company, they decided to store their password in database in plain text format, but that's not the proper way technically. When you think about it, it's not the proper way. There are widely accepted methods for it. Normally, many of you are familiar with this. Normally what we do is we use something called hash function in order to store password in database, right? Hash function is something you have some huge amount of information, then you create a digest by sending this data set to a function. So no matter how big or small is your data set, original data set, your digest stays the same size, and you can't reverse it. By starting from the digest, there is no way that you can calculate the original data set that was used to compute the digest. That's the nature of hash. It's only one way. It only goes one way. There is no function to reverse. So there are various hashes. There are various hash functions, a number of hash functions. These are the most popular ones that we use in the industry. In default, NTLM is used by Microsoft in order to hash Windows password. other things are familiar to us, SHA1, SHA256. CRC32 is mostly used in electronics. For example, disk drives. In order to error check this CRC stands for cyclic redundancy check. It's basically polynomial. Look at this MD5 password. Oh, hello. If you slightly change it, the generated hash is completely different. So, how do we go to hash to password? Think about it. So we got hold of someone's database. All the passwords have been hashed. So how do we generate original password starting from the hash? There is no methodical way to go back from hash to the original password. Right? There are number of ways. We can only go forward. But if we are clever, we can use that to generate the original password. So how do we do it? First one is dictionary attack. We construct huge list of possible passwords, various names, previously had passwords, huge list of words, basically word list, right? Then we take one word, compute the hash, and compare it with the hash that we want to crack. If it matches, that original word we got to compute the hash is our password, right? So we can write a program to compare millions of billions of passwords like this. So probably, if you are lucky, something may match or may not. Other thing is brute force. Then what we do is we try all the possible combinations. For example, if we are trying to find 4-character passwords, we can generate all the possible combinations of 4-character passwords and then check one by one. It takes time, right? But we can do it. Another thing is lookup table. So what did we do previously is we took a password from a list, computed the hash, then checked. But without doing that, if we have the password list, we can pre-compute the hashes. We can, in advance, we can compute the hashes and store the hashes with the password themselves. Then it problem reduced to a lookup problem, right? Then we have a hash, we just look up in our list whether we have this hash in our list. If we have the hash, we can just take the corresponding password. Right? This is faster because we don't have to calculate the hash. We have previously calculated it that stored against the password. Other thing is rainbow table. So this lookup table can grow rapidly, right? If you have billions of passwords, if that list is huge, this lookup table can grow very rapidly for hundreds of gigabytes. So people found some mathematical way to reduce the size of this table. That's called rainbow table. But it is actually a lookup table, kind of sophisticated lookup table. Another thing is reverse lookup. What is reverse lookup? We guess a password, then compute its hash, and then try to find all the users having that hash in the hash database. Right? That's called reverse lookup. We may find a number of users using that hash we are trying to make, or we may find no one. As we go through the list, we can recover some users. So these are the basic methods that we can start from a hash and generate its corresponding parser. So here we assume that database is storing the hash alone without any other process, right? You take the user's password, make a hash, and then store it in the database. If that has happened, if that's the case, we can do all sort of things like this, especially these lookups, right? There's a way to prevent this. Right? If you think about this brute force attack, there is no way to stop it. We can only make it difficult. Right? So we can take various measures to make it difficult. One thing is sort. What we do is we create a random string like this, concatenate it with the password, and then make the hash. Right? Even if two users are using the same password, because of their sort is different, they end up with two different hashes. Otherwise, what will happen is, if two users in your database are using the same password, we can observe the same hash. If one hash is found, you can automatically get the hash of other user who is using the same password, right? If you are using sort, that can be prevented. Because this sort is generated randomly, and it is concatenated with the password and then makes the hash. So two people using same password will end up with two different hashes. And this sort is stored in the database with the hash itself. We don't need to hide the sort. We are just storing the sort in the database. Normally this is the widely accepted way of storing password in a database, right? So now there are some software that we can use to automate this process. You start from hash and do some guesswork, and then find the original password. So this process can be automated. There are some software written for this process. One of those software is this Hashcat, and there are a number of other software. For example, John the Ripper or something. So this Hashcat is very popular among password cracking software. So here I am explaining the various parameters, right? Now I am going to run this Hashcat in my laptop and see what happens for a simple password with length of 6 characters, and it will only contain lowercase letters and numbers. Otherwise it will take time. We don't have much time to make clear. So I will choose short password. Just look at these numbers, parameters, right? N8 means it creates 8 threads. So this processor has 4 cores. Each core has 2 hardware threads, and OS sees it as 8 different threads. Also, hash mode is 1410. That means what the hash we are trying to break is created like this, right? Password plus some sort. They send a number of different attack modes: brute force, table looking, rainbow tables, dictionary attacks, like that. And we can give the character set. So what I have given here is the character set that we are going to work on. Consists of letters and digits only. Lowercase letters and digits. Right? So we can control the character set with this parameter. We can give up to 4 character sets. This file contains the hash that we are trying to break, and this is the mask. I'm going to do mask attack. So with this, we are telling the software our password is 6 character long, right? Each letter of this password is taken from this character set. Right? So we can adjust this. There are inbuilt character sets. We can, if you want, we can tell the software, okay, first letter of this password is always uppercase. Then we put here question mark U. Like that, we can control the nature of password which we are going to create. And look at this. Only lowercase letters and numbers, right? 26 letters plus 10 numbers, 36 to the 6th power. It's about 2 billion combinations, right? If it can include uppercase letters as well, it will come to 56 billion combinations. It's a very large value, right? Not trivial, not very small. This will take about 1 minute on my laptop. Hashtag 8 threads. Attack mode is brute force. Here we are going to crack SHA-256 with generated by concatenating password and salt. This is the character set and this is the mask. So this hash file, I'll show you the hash file. So it contains the password hash and the sort separated by code. Look at the speed, 18.90 million words per second. Look at how it's using the processing, all the 8 cores. This will take, remember this number, right? 18.9 million words.
Strictly checks the password length is 6.
Yeah.
Nothing from 1 to 6.
No.
Strictly.
Yeah.
So you know the length already.
Yeah. You can configure it.
Right,
So in order to save time,
yes.
I'm
In this example, you are looking at fixed length.
Fixed length. That's correct. So the password is ABC1. Now I want you to come up with any password, 6 character password with lowercase letters and digits. I have created a small script to generate hash and a sort. So someone come here and type the password, 6 character password. Don't type the password you are using. Anyone?
That's the most popular password in English.
Saling.
Don't type. It's your friends.
Don't press enter.
It's lazy very Maragat type.
Type the hardest password possible. But stay within the limits. Only 6 characters, lowercase letters and numbers. That. I will add some random salt as well. This is the salt. Okay. Now it has generated hash.text file with the password hash and the salt. I will share the file just to make sure. It contains them. Let's try to crack it. Everything is in order. If it is not cracked, it's Salinger's fault, not mine. This is your password, is it? So it took only about 1 minute. Here. Started at this time and ended at this time. It was done without any special hardware, using my laptop. So if you use uppercase, if you allow uppercase letters, the number of combinations will go up to 56 billion, and it will take some time, few minutes, 15, maybe half an hour, but it will do the job eventually. So let's look at these attack types in detail. Right? First type is dictionary attack. You have a list of words. You take words one by one, generate the hash, and then check. Others is dictionary plus rules attack. You have your dictionary. You take one word, and using number of rules, you generate set of other variations of this word. You take ABC, and you generate this list from ABC. ABC itself, this should become BAC, right? Then ABC1, ABC12, hash ABC, like that. From one word in the dictionary, using some rules, you can generate, you can expand one word. into number of variables and then check, right? The other is hybrid pattern. You take one word and you append all the possible combinations of two numbers and some pattern here, right? In this particular case, we are appending two numbers and all the possible combination of those two numbers into this word. Right? Other thing is mask attack. This is what we just did. And other thing is just brute force, trying everything. Now, if you look at this, this is very interesting. Dictionary plus rules attack, right? I'll show you that term. Now I'm going to right. Now we have a dictionary here, test word list. It contains only one word, ABC, right? Just to demonstrate the concept. Now, what I'm going to do is, I'm going to create a password, create the hash for password ABC123. Make this ABC123. Created the hash. Go there. And do a dictionary. With a rule set. So this is our rules file. This file says the software how to modify a selected dictionary word. You have to append this number at the end, then this number at the end. You have to reverse and check like that. There are a number of rules in this file. This is the rules file, right? Use the password as it is, use the selected dictionary word as it is, reverse it, make it uppercase, append it 0, 1, 2, 3, like that, append it two numbers like this. So it has about 74 different rules on telling the software how to modify the selected dictionary word to make its variants. So we only have ABC in the dictionary. Our password is ABC123. Now we are trying to make a dictionary attack with rules. Done. ABC123 is cracked. Right? But our dictionary only had ABC. It created the number of variants and then checked. So far we used our machine, our CPU, but there's other much better way of doing this using a graphics card, right? This is ATI graphic card 5770. Machine with this graphic card was given to us by Sumith for this demonstration. This is his gaming machine. Normally graphic cards are used to generate computer graphics, right? To play games and things like that. So how can we use a graphic card in order to crack passwords? If you think about it, these hashing algorithms, right, is doing same thing over and over again on a large set of data. These graphic cards are designed for exactly that. Right? It can do things parallelly, at very high speed, on very large set of data. Let's see. Look, this is the actual graphic chip in this card. This is, I think, US penny, right? Roughly about 50 cents. So, if you are doing work with CPU is true, it has limited number of hardware threads, but it's basically doing things sequentially. Take one problem, solve it, then goes to other problem, then goes to other problem, like this. It's doing things sequentially. It may have limited number of threads to do things parallel. We may create thousands of threads, but only the number of threads allowed by the implemented in hardware that's supported by a chip, in this case 8, are running truly parallel, right? Other threads are running sequentially. One after another. Not actually sequentially. OS may schedule threads in different manner, normally round robin, but when one thread is running, all other threads are suspended, unless allowed purpose. Right? If you processing units, number of small processing units, large amount of processing units that can run these small tasks parallel. That's why graphic cards are very powerful. So how do you solve this problem using graphic card? Now we have a hash and create a set. So basically we have a function that we need to execute on a large set of data. We first copy data set into the graphics processor. Right? Then copy our code into the code space and execute it. Graphic processor execute our code on this data set parallelly inside. Then we take the output back. That's how we do it. So all the processing part happens inside the graphics processor itself, right? The code we are going to execute on the data set is called kernel. Right? We make a kernel and load it to the code space, load our data, execute the kernel on data, then take the output back. So this is that particular card, 8770. This is how it is arranged inside the die, right? This is the area we execute our code. It has 10 compute unit. This row is called compute unit. It's like this, right? It contains 16 stream cores. This is called one stream core. 16 of them in this one compute unit. And if you look at one of these items, it contains 5 processing elements. Right? These are little processing elements. It has its own memory and branching unit, etc. So this card has about 800 processing elements. Right? This one element is like a small processor. It can execute a small code. In addition to that, it may contain some other support electronics. L2 cache is there inside the card, so that it can manipulate data very fast. Also, there's an outside memory controller, and this memory is placed outside the card, outside the processor in the card. Right? It may contain 512 or 1 GB memory. But you easily load the data into the memory and run the kernel. So kernel, each and every kernel is run inside one of these processors. So you have 800 parallel processing units in the graphics card. Some person has created this 25 GB cluster. It contains 25 graphic cards, right? He was able to do this. He is using the exact same software that we are using here. I will demonstrate to you in few minutes. He can do 63 billion guesses against SHA-1, 180 against MD5, 350 billion guesses per second against Microsoft NTL, right? Every possible 8-SHA password is cracked in 6 hours. Every possible combination. How many combinations? This many. I can't read this. Right? In order to do a comparison, this is a light year. You know what a light year is, right? the amount of distance light travels in a year. This is light year in meters. And this is the number of combinations this machine can track in 6 hours. This machine can guess in 6 hours. Right? Very close. So this is one server. It has about 8 graphic cards inside. So let's track some parcels in GPU. Same software that 25 GPU cluster is using. This is a special version of Hashcat optimized for graphics card. Now I am going to do the same thing here. Password with lowercase letters and digits only. 6 character long. Same attack mode, brute force, and the mode is 1410. That SHA256 is password plus solve. Done. We had 16 million here, right? When we were cracking this password in laptop, we had only 16 million guesses per second. We had this 323.9 million hashes per second. It's not using the letters, uppercase letters and numbers, 6 character long. So I have modified the character set here. It contains lowercase letters, digits and uppercase letters as well. 6 character long password and different hash path. $319.7 million hashes per second. How many possible combinations for this one? Anyone? Can you remember? 56 billion, right? Status. That doesn't less. Can you hear the fan? The processor is heating up.
Did the mean say he wants the computer back?
Okay, done. This is the password, the capital is it, right? Done in about 2 minutes. So, with the speed of roughly 300 million hashes per second. Now, let's try to do, this is SHA256 is a bit heavy, right? Let's try to do MD5 and see what happens. So we have MD5 hash in a file, right? What we will do is hashtag number of threads 8, attack mode, the hash mode is 0 for MD5. And attack mode is 8, brute force. Character set is lowercase letters and English. MD hash is our hash file. We have to try the mask. 1, 2, 3, 4, 5, 6. 66 million per second. Right. I think this one contains uppercase letter as well. So this will take some time. I'm not going to make you wait for this. I just wanted to show you the speed. 66.56 million. Now let's do the same here. This is going to be 0. Done. Let me guess. 2 billion hashes per second. 2.3 billion. Right? This says 2000 million. This is also done, right? At 67 million. So you can easily see the difference, right? So this hardware is becoming very powerful day by day. If we can do this at 2 billion hashes per second, then a truly determined person with a lot of resources can do a better job. We can even crack 6-character password with full brute force using our laptop and do better job with graphic card. So how do we prevent this? We can't prevent brute force attack. We can only discourage people from doing that. So there are some special algorithms for it. Right? This is one such algorithm. This is actually not a hashing algorithm. This is key expansion algorithm. This HMAC is key expansion algorithm. BKDF2 stands for password-based key derivation function. Right? It is specifically developed to make this kind of cracking hard. So how do they do that? Right? What it does is it takes our password and the salt, and it sends it through this HMAC SHA256. SHA256 is a hashing function. HMAC means hash-based message authentication code. Right? This mixes up this password and the salt. It combines these two and create another hash value. Right? Then at the next step, it takes this hash value and password, you create another, right? It's doing this all the way. The number of such stages we can configure. At the end, it is going to XOR all these intermediate outputs and then create the final hash. So this algorithm accepts a work factor. Work factor means number of iterations. So we can configure number of iterations. As of November 2013, accepted value is 10,000. What we do is we provide number of iterations, sort and the hash to this function, create the hash and store iteration count, sort and the hash in the database. Right? So we have to re-evaluate iteration count yearly. So year by year the hardware becomes more powerful. So we have to re-evaluate the iteration count yearly and change the iteration count according to current hardware trend. So there are other two algorithms like this, decrypt and scrypt. Actually, we are using this one in ATN. Right? This is what we do in order to hash online user data. But our iteration count is, I think, 11. It's not enough. We have to make it 10,000 or more. This is very interesting. This is hardware cost to crack hashes in average 1 year. This is the cost that will take to build hardware that can crack these hashes in 1 year. Right? This is 1 year is average value. It will take 2 years to go through the entire set of combinations. Right? Discrete, you can create such hardware in less than $1 by spending less than $1 for 6 character letters. When it goes up, it is still less than $1 here. That's why you should use this. This is very hardware friendly. You can implement it in graphics processors. You can create dedicated hardware. This is MD5, and this is our function that we talked about. What is this value? This 100 milliseconds. When we keep increasing that work factor, number of iterations, it takes some time to create the hash. Right? We can make it several 100,000 because if you do that, it will take several seconds to create the hash. So we have to balance out this work factor. Normally accepted value is it should be able to create a hash within 10 milliseconds. So it depends on the server we are deploying code. If you are using very powerful server, we can probably increase the work factor a bit high. So this is 100 millisecond version. Now work factor has been adjusted so that the password is created, hash is created within 100 milliseconds. Actually, we have to provide the kind of hardware it's using. They haven't provided it anyway. So for 10 character password, in order to create a custom hardware to break this key, it will take $160 million. If it is 5 seconds, it will take $8.3 billion, like that. So how did they come up with these numbers? Using these statistics, right? 1 gate. So these digital electrons consist of logic gates, right? 1 gate cost 1 gate is about take about 5 square micrometers of VLSI area, like that. VLSI circuit cost $0.1 for a square millimeter. Then using these values, they can calculate these. Just to show you We have to stick with these password creation, hash creation functions. That's it. I think you learn something new, but don't try to crack hard the hash passwords using this knowledge. This is truly for educational purposes only.